Welcome. Today we'll explore how CSE Cosmological Self-Equilibrium and CEC Cosmological Equilibrium Constant offer a fresh lens for understanding problem-solving strategies from neuromorphic computing to everyday challenges. Think of CSE as a measure of imbalance like the tilt under a marble, and CEC as the local force or gain that pulls things back to equilibrium. This dynamic duo isn't just for physics or neuroscience, it's a universal principle that can be mapped onto nearly any method of tackling problems. Let's walk through each classic strategy and see how CSE-CEC brings new clarity and control. Every effective problem-solving journey starts with understanding the problem itself. In CSE-CEC terms, CSE is your diagnostic tool. It measures how far your current understanding is from the true problem statement. If you're unsure about the requirements or missing key details, your CSE is high. CEC, on the other hand, is the corrective energy you apply. The more uncertainty, higher CSE; the more effort, higher CEC you invest in clarifying the problem. This could mean asking more questions, reviewing definitions, or re-examining the data before moving forward. The process is dynamic. As your understanding improves, CSE drops and CEC relaxes, letting you proceed. Visualization is a powerful tool. When you draw a diagram or sketch a scenario, you're translating abstract information into a concrete form. Here, CSE measures the gap between your mental model and what you can visualize. If you can't picture the relationship, your CSE is high. CEC then determines how much visualization energy to invest. Should you make a quick sketch or build a detailed simulation? As your picture becomes clearer, CSE drops and CEC can be dialed back. This adaptive process ensures you don't overinvest in unnecessary detail, but also don't miss critical connections. Sometimes problems are too complex to tackle head-on. Simplification is about stripping away unnecessary details. In CSE-CEC language, CSE quantifies the complexity or overload, how many moving parts or variables are overwhelming the process. CEC is the force you apply to reduce the complexity, deciding how aggressively to prune features or focus on essentials. If CSE is high, CEC ramps up, leading you to make bold simplification. As the problem becomes more manageable, CSE falls and CEC eases off, allowing you to focus on the core challenge. Working backward is a classic strategy. Start from the desired outcome and reason in reverse. Here, CSE is the distance between your current state and the goal. The larger the gap, the higher the CSE. CEC determines how much effort you put into backtracking. Should you take small, cautious steps or make bold leaps? As you get closer to the goal, CSE drops and CEC can be reduced, making the process more efficient. This dynamic adjustment ensures you don't waste energy when you're already near a solution. Breaking a big problem into smaller, manageable parts is often the key to progress. In this context, CSE acts as a global stress signal. If the overall problem feels overwhelming, CSE is high. CEC is then distributed locally. Each subproblem gets a share of the corrective energy based on its own local CSE. This mirrors how the brain or a distributed system might allocate resources, focus more energy where the imbalance is greatest. As each part is solved, local CSEs drop and the global CSE follows, guiding the process to completion. Some problems are best solved by identifying what stays the same and invariant. Here, CSE measures how much a candidate solution or operation violates the invariant. If you're far from preserving it, CSE is high. CEC then acts as a penalty or weight, pushing you to stay within the invariant preserving space. This approach is especially powerful in algorithms and physics, where conservation laws guide solution. As you approach the invariant, CSE drops and CEC can relax, letting you focus on other aspects. Testing the limits, trying very large or very small cases, can reveal hidden patterns or weaknesses. In CSE-CEC terms, CSE is the deviation you observe as you push parameters to extremes. If the system behaves unexpectedly, CSE spikes. CEC then determines how far you push these extremes. Should you keep exploring or pull back? This method is especially useful in optimization and physics, where edge cases often expose the true nature of a problem. As you learn from the extremes, CSE guides you back to the typical regime. Symmetry can simplify problems by reducing the number of unique cases. CSE measures any asymmetry, how much two supposedly symmetric parts differ. If there's a big difference, CSE is high. CEC acts as a restoring force, encouraging updates or corrections that reimpose symmetry. This is common in physics, math, and even neural networks, where symmetry can lead to more robust and generalizable solutions. As symmetry is restored, CSE drops and CEC can be reduced. Solving small, concrete instances of a problem can reveal general patterns. Here, CSE is the mismatch between the solution to a small case and the expected general pattern. If the small case doesn't fit, CSE is high. CEC then determines how much analytic reasoning or further testing to apply. If small cases show structure, CEC increases to encourage deeper analysis. If not, CEC drops and you might switch to brute force or another approach. This iterative process helps build intuition before scaling up. Sometimes you just have to make a guess and see if it works. CSE here is the error or mismatch between your guess and the actual solution. CEC is the magnitude of corrective action you apply after checking. If the guess is close, CEC is low and you fine-tune. If it's way off, CEC is high and you might try a completely new approach. This feedback loop ensures you don't get stuck on bad guesses and can adapt quickly as you learn. Algorithmic approaches, CSE can be seen as the residual error or loss at each step, while CEC is the learning rate or gain that determines how strongly you update your solution. For example, in gradient descent, CSE is the gradient, how far you are from the minimum, and CEC is the step size. As you approach the solution, CSE drops and CEC can be reduced to avoid overshooting. This dynamic adjustment is key to efficient and stable convergence. Let's revisit neuromorphic computing, where CSE-CEC originated in this context. Here, CSE is the local imbalance between excitation and inhibition in a neuron or circuit. CEC is a local controller that gates plasticity or excitability. If CSE is high, CEC modulates learning or firing rates to restore balance. This mechanism has been shown to improve stability, sparsity, and sometimes accuracy in toy experiments, as seen in the DVS moving dot demo. The principle is biologically plausible and hardware-friendly. Thermodynamic or Ising-style computing, CSE maps to local free energy gradients or imbalance in detailed balance. CEC becomes a local temperature or coupling strength that controls how quickly the system relaxes to equilibrium. By modulating CEC, you can steer the system toward optimal solutions more efficiently, balancing exploration and exploitation. This approach is natural for simulated annealing and Boltzmann machines. Quantum computing, especially in adiabatic or annealing models, fits the equilibrium computing framework. CSE can be seen as the local imbalance between Hamiltonian driving terms and decoherence. CEC is the local controller, tuning couplings or dissipation to guide the system toward its ground state. While this mapping is less direct for gate model quantum computing, the principle still offers insights for engineered dissipation and error correction. Recent theories suggest the brain operates like a diffusion model, balancing noise and signal. Here, CSE is the local signal-to-noise ratio, and CEC is the gain that modulates either the amount of injected noise or the strength of corrective dynamics. This adaptive control helps maintain equilibrium, allowing the brain to denoise and adapt efficiently. The same principle can be applied in artificial diffusion models for generative AI. Equilibrium, as described in your document, is like a Higgs boson for equilibrium, a local field or quasi-particle that enforces or signals equilibrium. CSE acts as the source field that perturbs the order parameter, while CEC is the local coupling or susceptibility that determines the system's response. This analogy helps bridge concepts from particle physics, condensed matter, and neural computation, offering a unified language for equilibrium dynamics. CSE and CEC can be modeled as fields, spatially and temporally varying quantities, or as energy densities. CSE is a local imbalance field like excitatory minus inhibitory current or a local score. CEC can be a gain field multiplicative controller or an energy density that determines how quickly the system relaxes to equilibrium. This field-theoretic view enables the use of powerful mathematical tools from physics, such as gradient flows, Lagrangians, and response functions. Robotics, CSE can represent the difference between desired and actual states, like position or velocity, while CEC is the local gain applied to control loops. When the robot is far from its target high CSE, CEC increases, making the controller more aggressive. As the robot approaches its goal, CSE drops and CEC relaxes, saving energy and reducing overshoot. This adaptive control is key to efficient and robust robot behavior. Reservoir computing, CSE can be the local divergence or instability in the network's activation, while CEC is a damping or gain field that stabilizes the system near the edge of chaos. By tuning CEC based on CSE, the reservoir can maintain high memory capacity and robustness, adapting to changing inputs without becoming unstable or unresponsive. Analog hardware, CSE can be the mismatch or noise relative to the desired operating point, while CEC is a programmable bias or local temperature control. By adjusting CEC in response to CSE, circuits can conserve energy and reduce noise, maintaining reliable operation even under varying conditions. This principle is crucial for building robust, energy-efficient hardware. Synthetic biology, CSE can be the imbalance of reactant and product concentrations, while CEC is the local catalytic activity or enzyme expression. By modulating CEC in response to CSE, biological circuits can maintain homeostasis, stabilize outputs, and reduce metabolic load. This adaptive control mirrors natural homeostatic mechanisms in living systems. Collective systems like swarms or soft robots, CSE can be local stress or deviation from desired patterns, while CEC is the local damping or motility energy. By adjusting CEC based on CSE, the system can stabilize flocking patterns, reduce collisions, and control phase transitions. This principle enables adaptive, resilient collective behavior. Materials science, CSE can be the local deviation from order like magnetization or density, while CEC is the local susceptibility or defect energy. By controlling CEC, you can steer pattern formation, control domain sizes, and engineer self-assembly processes. This approach is powerful for designing new materials with tailored properties. In optimization, CSE is the local gradient or error, while CEC is the step size or temperature in simulated annealing. By adapting CEC based on CSE, algorithms can converge faster, avoid local minima, and balance exploration with exploitation. This adaptive approach is widely used in machine learning and metaheuristics. Bayesian inference, CSE is the prediction error or mismatch between beliefs and data, while CEC is the precision inverse variance or free energy density. By updating CEC in response to CSE, systems can adaptively weight new information, improving convergence and robustness to outliers. This principle underlies predictive coding in neuroscience and variational inference in machine learning. Reinforcement learning, CSE is the temporal difference TD error, how much the predicted reward differs from the actual outcome. CEC is the local exploration temperature or learning rate. By increasing CEC where TD error is high, the agent explores more or learns faster. Where error is low, CEC drops, consolidating stable behaviors. This adaptive mechanism improves sample efficiency and safety. Distributed systems, CSE is the disagreement or divergence between nodes, while CEC is the local backoff or retry energy. By increasing CEC when disagreement is high, nodes slow down or back off, preventing excessive churn and stabilizing consensus. This adaptive control is key to robust, scalable, distributed algorithms. In ecology, CSE can be resource imbalance or predator-prey mismatch, while CEC is the local carrying capacity or regulatory mechanism. By adjusting CEC in response to CSE, populations can adaptively migrate, reproduce, or enter dormancy, maintaining ecosystem balance and reducing extinction risk. In traffic systems, CSE is local congestion or imbalance in flow, while CEC is the variable speed limit or signaling energy that damps flow. By increasing CEC in congested areas, the system can smooth traffic, reduce jams, and improve throughput. This principle is used in smart traffic control and crowd management. Powerful design is to make CSE a global signal, measuring system-wide imbalance or error, while CEC is a local controller that uses both global and local information to act. This mirrors biological systems where global neuromodulators set the overall tone and local circuits fine-tune behavior. The combination enables coordination, robustness, and efficiency across scales. Imagine a marble on a landscape. CSE is the local tilt, the direction and size of imbalance. CEC is the local friction or stiffness, how strongly the marble is pulled back to the valley. Together they shape how the marble finds equilibrium, just like gravity shapes motion through curved space. In everyday life, CSE is the sense that something's off. CEC is how hard you work to fix it. This simple picture makes the abstract concepts of CSE and CEC intuitive and relatable. But if the cosmos itself is dynamic, its shape and size changing in response to CSE-CEC fields. In the speculative model, CSE is the local source of imbalance, while CEC or the equilibrium field modifies the geometry, making the universe's scale and curvature adaptive like an elastic sheet. This idea bridges information, energy, and geometry, suggesting that the universe self-organizes in response to equilibrium signals, much like an amoeba changes shape. CSE-CEC fields can locally warp geometry. The observable universe could, in principle, have an amoeba-like dynamic shape bulging and contracting in response to local equilibrium signals. While current observations require these effects to be small, the concept opens new avenues for thinking about cosmology, structure formation, and the interplay between information and geometry. Across all these domains, the core principle remains. CSE measures imbalance or error, while CEC is the local controller or energy that restores equilibrium. This framework unifies problem-solving strategies, physical systems, and even cosmological models, offering a powerful, adaptable language for understanding and designing complex systems. Whether you're building neural networks, designing robots, managing traffic, or exploring the cosmos, the CSE-CEC framework provides actionable guidance. Measure imbalance CSE, apply adaptive correction CEC, and let the system self-organize toward stability and efficiency. This approach is not only theoretically elegant but also practically effective across a wide range of challenges. Visualize CSE-CEC. Imagine a landscape with hills and valleys. The marble's position represents the system's state. CSE is the slope under the marble, telling you which way things are off balance. CEC is the stickiness or steepness, how strongly the marble is pulled back to a valley. This analogy helps make the abstract concepts tangible and memorable. Daily life, CSE and CEC appear everywhere. A thermostat uses CSE temperature difference to decide how much heat to apply CEC. A driver senses wind pushing the car CSE and adjusts the steering CEC. Even in conversations, noticing confusion CSE prompts you to clarify CEC. Recognizing these patterns helps you apply the equilibrium principle in any context. Learning systems, both biological and artificial, rely on CSE-CEC dynamics. When performance drops, high CSE, learning rates or plasticity CEC increase to adapt. As performance stabilizes, CSE falls and CEC relaxes, consolidating learning. This adaptive feedback loop is at the heart of robust, efficient learning in brains and machines. In teams, CSE can be the sense of misalignment or conflict, while CEC is the energy or effort devoted to resolving issues. High CSE prompts more communication and coordination, higher CEC. As alignment improves, CSE drops and the team can focus on execution. This principle underlies effective collaboration and conflict resolution. Creative processes often start with a sense that something is missing or off. CSE. CEC is the energy you invest in brainstorming, experimenting, and iterating. As ideas converge and the creative imbalance is resolved, CSE drops and CEC relaxes. This dynamic is at the heart of innovation and artistic expression. In health, CSE can be the body's signal that something is out of balance, like hunger, fatigue, or stress. CEC is the corrective action, eating, resting, or relaxing. By listening to CSE signals and applying appropriate CEC, you maintain homeostasis and well-being. This self-regulating loop is fundamental to life. In economics, CSE can be market disequilibrium, like excess demand or supply. CEC is the adjustment mechanism, price changes, production shifts, or policy interventions. As the market moves toward equilibrium, CSE drops and CEC interventions become less frequent. This dynamic underpins stable, efficient markets. Technological progress often follows a CSE-CEC pattern. New challenges or inefficiencies, CSE, drive innovation and investment, CEC. As solutions emerge and systems stabilize, CSE drops and the pace of change slows until new imbalances arise. This cycle drives continuous improvement and adaptation in technology. By recognizing and applying the CSE-CEC framework, you can approach any problem, scientific, technical, or personal, with a powerful adaptive mindset. Measure imbalance, apply targeted correction, and let equilibrium guide you to effective, resilient solutions. This principle is as universal as gravity, shaping systems from neurons to galaxies and from daily life to the frontiers of science.